Okay, in this video we're going to take a look at resonance. Resonance is important in several aspects of electronics, especially in radio communications. It's important in filters, oscillators, tuning circuits, and antennas, which are in this project. So we need to understand resonance. I'll start by explaining the concept while it applies to antennas, because I believe it is easier to understand it that way. That's how I first understood it. Then we can move to filters and tuning circuits. Now in my video titled Basic Electricity, Alternating Current, or AC Basics, I explained how AC current is generated and about frequency. This is a review of it. The faster a generator spins, the higher the output frequency gets. And the slower it goes, the lower the frequency is. So that demonstrates that current can cycle at different rates, known as its period, and measured in cycles per time period, usually per second, indicated as hertz. 1 hertz is 1 cycle per second, as 200 hertz is 200 cycles per second, and 1,000,000 hertz is 1,000,000 cycles per second, measured in megahertz. So if you graph an AC signal from a mechanical generator, it would look like this: a circle. 1 cycle is from the start of the wave at 0 degrees. It will rise to a peak at 90 degrees, then continue on to 180 degrees. From there it goes to 270 degrees, commonly known as -90 degrees. Then returns to 0 or 360 degrees. This completes 1 cycle. If you fold the circle out to make a graph as shown, you get this. Similar to a sine wave, with degrees from 0 through 180 above the line, then 180 to 0 with negative numbers below the center line, since the voltage or current changes direction. So above is positive and below is negative. The number of cycles that you can fit in a second determines the frequency, which is displayed as horizontal length on a graph between 0 degrees to the next 0 degrees on the graph. Now let's consider a single wire or tube antenna with its input at one end. You put a signal into the antenna. If you could visually see the signal radiate from the wire like this, that signal could be measured with a tape measure from the start of 1 cycle to the end of the cycle, and you'd be measuring the wavelength, which is commonly measured in meters, sometimes in feet. Here's a formula, where wavelength in meters equals 300 over frequency in megahertz, or wavelength in feet 492 over frequency in megahertz. So if we take a frequency of 440 megahertz and run it through the formula, we get 0.681 meters, converted to 68.1 centimeters. So your electrical length of your antenna is about the actual length of the radio wave. So if you make your antenna 68.1 centimeters long, it should be resonant at 440 megahertz. Doing one more at 28 megahertz, the result is 10.7 meters or 17.5 feet. For 1 cycle, you'd be standing 10.7 meters or 17.5 feet away from the antenna. Thus, if you make your antenna 10.7 meters long, it would be resonant at 28 megahertz. So your electrical length of your antenna is about the actual length of the radio wave. The longer the wavelength, the longer the frequency, or the shorter the wavelength, the higher the frequency. Now let's look at a model to get some kind of visual understanding of what this could look like in a circuit or in an antenna. Let's consider a single wire or tube antenna with its input at one end. Here we have 3 tubes. You see the center tube is the longest. The top tube is half the length of the center tube, and the bottom tube is some other length. We'll set our transmitter on the left end of each antenna to insert a signal at a specific frequency. The frequency is set so the transmitter pushes a wave at equal intervals so that on the center tube it pushes a new wave every round trip of the wave. The other 2 transmitters are set at the same frequency as the center tube, so all 3 of the transmitters fire at the same time. The first trip is on the positive part of the cycle. The return trip is on the negative part of the cycle. So the signal is pushed out of the transmitter as a wave indicated by the RAM appendage from the transmitter. The blue oval is the wave front. Things to watch for in this. The transmitters emit at the same time and same number of times. The wave fronts move at the same speed. And the wave fronts in the top and the middle antenna end up even and end up hitting the same ends of their respective antennas at the same time, just when the transmitters fire again. The bottom antenna ends up with an extra wave front because the original wave front was not at the end when the transmitter emitted its wave. On the bottom one, over time, more and more waves will be generated out of sync with each other. This is a problem with that in terms of a condition called SWR, or return loss. With 2 or more wavefronts out of sync, they interfere with each other, and this generates heat, which can build up in the transmitter and burn it out. It turns out the top 2 antennas are resonant at the same frequency, even though they are not the same length. This has implications in circuit design, especially with antennas. Okay, in another video we will explain how resonance works in circuits such as these, and what this means. I hope this video is useful, and please like and subscribe. Thank you for watching, and check out these videos. Thank you again.